Optimization. Optimization is used in max-min problems. So if somebody is going to manufacture something, they're looking for what is the best size, what's the maximum size or the minimum size when they're creating that object. So they might be looking at the area or the volume of certain shapes that they're producing in order to maximize the volume so that they get the most out of the cost of the object. So guidelines for max-min problems are that we write the equation using one variable, and this usually includes substitution. We take the derivative of the equation. We determine the critical numbers, and the critical numbers are substituted into the original equation. And we determine if the critical numbers are a max or a min as they apply to the problem. So in example 1 here, I have that a regular observation deck is built overlooking a courtyard. Find the dimensions of the deck if the area is to be 100 square meters and its perimeter is to be a minimum. So we know that area of a deck, area would be length times width. So in that deck, then the perimeter is 2L plus 2W. We need to change the area formula so that we use one variable. So W equals 100 divided by L. I chose to solve for W. And then I substitute what W equals into the perimeter formula of 2L plus 2W. So where I have the W highlighted in black, I'm going to place 100 divided by L. And since L is in the denominator, I move it into the numerator with the exponent -1. So now my perimeter equals 2L plus 200L to the -1. And you can see here that I have one variable. Now I'm going to take the derivative of P, the perimeter. So when I take the derivative of P, 2L becomes 2, and 200L to the -1. So I take the power of -1 and multiply it by 200. So that equals -200L to the -2, because I subtract 1 from the exponent. Since L has a negative exponent, I move it into the denominator. And now I need to solve for L. So 200 divided by L squared. I place it on the right-hand side of the equal sign so it becomes positive. Cross multiply, so I have 2L squared equals 200. Divide by 2 to both sides. Take the square root of 100. And L will equal plus or minus 10. Now since I can't have a negative length, I need to reject the -10, and my length is 10. So if I go back to my area formula of length times width for area, if the area is 100, that means that my width is 10 meters as well. So both the length and the width equal 10. In example 2, I have equal squares are cut off at each corner of a rectangular piece of cardboard 8 inches wide by 15 inches long, and an open top box is formed by turning up the sides. Find the length x of the sides of the square that must be cut off to produce a box of maximum volume. State the maximum volume of the box. So what I know that volume of a box is length times width times height. And I've drawn my diagram below where my width was 8, my length was 15, and I've cut out in each corner the length X out of the side so that I can turn up that box. And if you haven't done this before, you should actually take a piece of paper, cut out little X by X in the corners and fold up that piece of paper, and you'll see that you get an open box when you fold up the corners, up the sides of the box. So that means that my width, since I've cut out X from each corner, my width now becomes 8 minus 2x, and my length is 15 minus 2x. My height is x because I've turned up those sides, forming a box. If I substitute the length, width, and height into the volume formula so that I have a equation that includes just x, I'll have v equals 15 minus 2x in brackets times 8 minus 2x for the width times x for the height. I multiply by doing FOIL with the first two brackets, distribute the x inside as well and combine like terms. My volume with one variable x is now 4x cubed minus 46x squared plus 120x. Now that I have my volume formula, the next thing I'll do is take the derivative of the equation. So the derivative of the equation becomes 12x squared minus 92x plus 120. And if I solve that to find the critical numbers, I factor out a GCF of 4, divide by 4 to both sides, factor the trinomial, and I get x equals 5/3 and x equals 6. Now the reason I reject x equals 6 is if I go back to my original where I had length, width, and height, if I substitute 6 back in, 6 is too big, right? It ends up giving me a negative width, and I can't have a negative width because we can't have negative measurements when we're dealing with length, width, height, or volume area. You can't have a negative length. So 6 gets rejected. So the only value I have for x is 5/3. Now it says that I want to produce a box of maximum volume. State the maximum volume of the box. So I have to look to see if 5/3, my critical number 5/3, actually is a maximum point. So if I'm looking to see if it's a maximum point, then I need to plug it back into the equation. If I plug 5/3 back into the original equation, I get a volume of 90.74. If I check to see that it is a maximum point, I select 0 on the left and 2 on the right because 5/3 is above 1. And I look to see if it's increasing. So with 0, by substituting 0 in to the derivative, it equals 120. So that's a positive value, which means that it's increasing. If I sub in 2 into the derivative of 12x squared minus 92x plus 120, and I substitute 2 in for x, I see that I get a negative value. So 5/3 is my maximum point. So my maximum volume is 90.74. And it would be inches cubed.